I'm going to be talking about the nomenclature of alkynes. So just the basics, an alkyne is a hydrocarbon with at least one triple carbon-carbon bond, and all triple bond carbon atoms are sp hybridized. This means that their molecular geometry is linear, and linear is 180 degrees. There are two types of alkynes, being internal alkynes and terminal alkynes, and I'll talk about those in better detail in the next slide. Alkynes also cannot have easy isomerism as compared to alkenes, which do. On the right, I also made a chart that just shows the basic nomenclature of alkynes, starting with a 2-carbon long chain all the way down to a 10-carbon long chain. So when talking about the difference between internal alkynes and terminal alkynes have no hydrogen atoms bonded to triple bonded carbon atoms. So you see in this example, we have our triple bond, but then we have an R group on the right as well as an R group on the left. With terminal alkynes, there's at least one hydrogen atom bonded to a triple bonded carbon atom. So our triple bond carbons are here. We have an R group on the left and then a hydrogen on the right. So here are some basic examples. We know that when naming alkynes, since those are triple bonds, the ending will be YNE. When naming alkenes, since they're double bonds, the ending is ENE. And then with alkanes, because they're single bonds, it's ANE. So see with this triple bond, we already know the ending is going to be YNE. And because there's 2 carbons, we know it's going to be F. So then therefore, this will be ethyne. Then with this example, let's count the carbons, 1, 2, 3, 4, 5, 6. So we know it's going to be hexyne, because it's a triple bond. And the triple bond begins on carbon number 2. So it's going to be 2-hexyne. And also, this is going to be an internal alkyne because of where the bond is located. In this example, we count the carbons, 1, 2, 3, 4, 5, 6, 7. So we know it's going to be heptyne because it's a triple bond with 7 carbons. And then the triple bond begins on carbon number 1. Therefore, the name is going to be 1-heptyne, and this is also a terminal alkyne, again, because of where the triple bond is located. So I found this first example to be very important because we also have to remember our priorities. We know that hydroxyl is number 1 priority, then alkynes, then alkenes, then alkyl and halogen groups. So instead of numbering the carbons left to right, which some might do, we have to label it right to left. So it'd be 1, 2, 3, 4. And 4 carbons would be butene. So in number 2, we do have our alcohol group. So when naming it, we have to put that at the end of the name as 2-ol, O-L. Then on number 3 is where the triple bond begins. So in the end, the name would be 2-butene-2-ol. Then in this example, count the carbons, 1, 2, 3, 4, 5, 6, 7. And this triple bond group has a higher priority than this methoxy group. So we would number the carbons left to right. And because there are 7 carbons, this would be heptyne. And then on the 5th carbon, we have our methoxy group. And on 2 is where the triple bond begins. So when putting it in alphabetical order, in the end, the name would be 5-methoxy-2-heptyne. So here are a few different situations. Here we have a halogen being fluorine and the methyl sticking out. So let's count our carbons, 1, 2, 3, 4, 5, 6, 7, 8. So that'd be octyne. We have a methyl on carbon number 2 and a fluorine on carbon number 6, and the beginning of our triple bond on 3. So after putting in alphabetical order, it would be 6-fluoro, 2-methyl, 3-octyne. Now in this example, you might be wondering, what should we do if there's 2 sets of triple bonds? So we would treat this just as if there are 2 sets of methyls, ethyls, and so forth. We would put the prefix di in front of it. So let's count our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we notice that on carbon 2 and carbon 6 is where the bonds begin, but then also from going left to right, the bonds begin on carbon 2 and 6. So then we have to find where the next substituent begins. So we see that there's a methyl here, so we would start from left to right. So since there's 8 carbons, it would be octyne. We see that on carbon number 4 there's a methyl, and on the beginning of carbon 2 and carbon 6 is where the triple bond starts. So when naming it, it would be 4-methyl 2,6-octadyne, like this. So then we have a few more different situations. Here we have a cyclopropyl, which I thought was important to include. So here we have our terminal alkyne. Let's count the carbons, 1, 2, 3, 4, 5, 6. On carbon 5, we have our cyclopropyl, and the bond begins on carbon 1. Therefore, after putting in alphabetical order, we have the name 5-cyclopropyl-1-hexyne. Now I use this example for last because I find it the most important. We have two sets of alcohols here, and we know that two sets is called a diol, and diols always go at the end of the name. And other than having this triple bond, we have a double bond. And with double bonds, as I said before, we do need to put easy configuration. So when finding the configuration of this double bond on the second carbon, it would be 2E. So now let's count our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. Make sure that you find the longest carbon chain because some students will end here and then call this diethyl. So we have our 8-carbon chain being octyne. On number 1, we have our alcohol, and then on number 6, we have an alcohol as well. On number 2, we have our double bond, and we know that when there's double bonds, the ending has to be octene. But we also do have our triple bond. So when naming the compound, we have 2E for the configuration, 6-ethyl, because this is the ethyl on carbon number 6. 3, we have our methyl. On 2, we have our double bond, so it'd be octene. However, we do have our triple bond on number 4, so it'd be octene 4-ine. And then because diols go last on carbon 1 and 6, it'd be 1,6-diol. In summary, now that we know the nomenclature of alkynes, we know that they will always have linear molecular geometry at 180 degrees. We also know that alkynes will never have easy isomerism as compared to alkenes, which do. So when you see a molecule with double and triple bonds, make sure to assign easy or cis or trans to the double bond. Also, make sure to find the longest carbon chain and remember their priority. Remember, priority goes hydroxyl, alkyne, alkene, then alkyl, and halogen groups.